This is our 7th computer session. The assumption is that you've been through all of the theory slides and you've worked through all the computer sessions up to this point. That will let us work through some sections of code that may be a little bit confusing if you've only seen it the first time, but it's covered in detail in earlier sessions. Also, I'm not going to stop to explain theory because that's in the theory slides, but we certainly will connect code to theory. Now, this computer session will very much parallel what we did in computer session number 4, where we generated two-dimensional spatially variant lattices. We're going to do pretty much the same exact thing here, except we're going to generate a three-dimensional spatially variant lattice. And the code parallels it very closely to the 2D lattices. There are some things that we'll do a little bit differently, and of course we have the third dimension to deal with. At the end of this, we will save our lattice to a file, and then in the next computer session we'll create an STL file and then load it into CAD or Blender again. So with that said, let's start off how we normally do. We will initialize MATLAB. We will close all the figure windows, clear the command window, and the most important one, clear memory. We'll define some units, in this case just degrees. And we'll use that just like we've done in previous computer sessions. We'll also open a figure window. And we'll give it a background color of white. Then we'll say we want to utilize normalized units. And that's because I don't know how big your screen is compared to mine. So as long as we're saying normalized units, we can just use things like zeros and ones to go full screen. Okay, so let's run this, make sure this works, and all that should happen, we should see a figure window come up, or we get an error and we have to fix it. Okay, so we're working. On to the next section, which is our dashboard, where we'll define everything about this code. All the hard-coded numbers appear in the dashboard, no work though. So here we'll define our unit cell dimensions. We'll just give it units of 1. And as before, 1 what? Could be 1 meter, 1 centimeter, could be 2.7 millimeters. But whatever the units are of A will carry through everything else where we use physical dimensions. We'll need some grid parameters. First, we'll define the physical size of our grid. We have a three-dimensional grid now, so we have a physical size in X. Let's just make it be 7 unit cells wide. We'll make the Y dimension also 7 unit cells, and we'll set the Z just to 1 unit cell. Now, this would probably be a prohibitively small lattice, but it will let things run quickly for this demonstration. We could simply just put bigger numbers here to generate a bigger lattice, but it would take longer to run. Just like before, we'll have an NRES low and an NRES high because we'll have 2 different grids, one where we do most of the work and we take the spatial variance all the way up to the grading phase, then interpolate to a very high resolution grid, and that grid needs to be high resolution because we probably have some very fast or high spatial frequency gradings, constituent gradings that have a very short period that we have to resolve. So, and particularly for 3 dimensions where our computer resources become even more limited, this low and high resolution grid scheme becomes very important, particularly if we want it to run reasonably fast. So that is it for our dashboard. The next section of code is to calculate our grids. So this will be the low resolution and high resolution grids, and this will parallel exactly what we did in computer session 4. So we'll start off with the low resolution grid. We'll calculate the grid resolution parameters, and that will be the lattice constant over NRES low, because that's how NRES low is defined. And we'll do the same thing for dy and dz. So that tells us the size of our voxel, if you will. Next, how many points is on our grid? We will round up the physical width divided by the cell size. But since we rounded up, NX, SX, and DX are a little bit inconsistent now. So what I like to do is just make DX a little bit smaller so that SX will equal NX times DX, and all three parameters are agreeing with each other. And we'll do the same thing for Y and Z. Sometimes I'm not sure if I save time by copying and pasting, but it makes me feel good. Okay, let's run this just to make sure we don't get any errors, to make sure there's no typos. And we can look at how big our grid will be. 70 points by 70 points by 10 points. So that's a reasonable size three-dimensional grid. Next, we'll calculate our axis vectors. And I like to center things around 0. Usually not needed, but it's a habit for me. And so we'll do this for X, Y, and Z. Okay, I'm going to run it, make sure there's no errors. Everything looks good so far. And then the last step here for the low resolution grid is to do the mesh grid. And there we go. So that is everything about our low resolution grid. Now we have our high resolution grid to calculate. So since we called the resolution parameters dx, dy, dz for the low resolution grid, let's call these dx2, dy2, and dz2. So we will define the grid resolution on the high resolution grid as A over nres high, just like what we did for the low resolution grid, but using nres high. We will calculate the number of points on this high resolution grid, which will be the physical width divided by the cell size. And we'll do this for Y and Z as well. On the MathWorks website, they say putting commands horizontally like this is bad practice in MATLAB. I don't know, for some reason I like doing it this way because it makes the code more compact. These are sections of code that I type all the time, so in my mind it's more pleasing that they're on one line than separated, but certainly feel free to separate them if that's what you want to do. Now from here we're going to do things a little bit differently to make our interpolation step a little bit easier. We will, just like we did for computer session 4, we will use linspace to create our axis vectors. So we'll start and stop on the same points. Our low res and high res grids will start and stop on the same end points. So we'll define an XA2, we'll use linspace. We'll say start at the same first point as the low resolution grid, end at the same end point as the low resolution grid, but use NX2 number of points. And we'll do this for X, Y, and Z. Okay, we'll run this, make sure there's no errors. Okay, very good. Now we have to recalculate the grid resolution parameters. Since we use linspace, they'll be a little bit different than we're expecting. So dx2 will be xa2 2 minus xa2 1. So we're just looking at the spacing between points. And we'll do this for x, y, and z. And then the very last thing is to create the mesh grid, which we may or may not need. In general, we're doing a pretty small three-dimensional grid, so it's not that big of a deal. But in general, if you don't need these mesh grid parameters, you really should not calculate them. So that is it for our grids. Let's run it, make sure there's no errors, and it looks like we're good. We're on to the next section of code. So in this next section, what should be done in general is we bring in a unit cell, we do a three-dimensional fast Fourier transform to do a Fourier expansion, and we end up with thousands and thousands of component planar gratings. Now this is certainly possible. I've done it, it works well, but it leads to a slow code because we have to spatially vary each of those in 3 dimensions separately. So in 3 dimensions, we really try to minimize the number of grading vectors or planar gratings. And we talked through a bunch of techniques of doing that. Another really good way that I seem to do a lot, maybe out of laziness more than anything else, but rather than come up with the world's best unit cell, expand it into planar gratings and try to reduce that set, instead what I'll do is I'll just pick 3 planar gratings, and whatever unit cell that provides, I see if that works. And if that works well enough for me, then I can expand my unit cell just into 3 planar gratings. And it turns out, if we look at the unit cell, we look at its symmetry, and calculate the reciprocal lattice vectors of that lattice, that would be our choice of our 3 grading vectors. And we can get all 14 of the Bravais lattices that way. And again, I'm not going to get into the theory of that, but in this case, we're just going to use a simple cubic unit cell. Which means we'll have our 3 grading vectors all at 90 degrees with respect to each other. So we'll have K1, its magnitude is 2 pi over the period. And we give it a unit vector pointing in the x direction. So K1 will point in the x direction with magnitude 2 pi over period. We'll have a K2 and a K3, and they'll point in the y and z directions respectively. And then we'll generate our list. So K list is simply K1, K2, and K3. Whoops, K3. And we need the Fourier coefficients, which we haven't calculated. So we'll just make each one unit amplitude. And that's our list of grading vectors. Okay, we are now ready to go on to our next section of code. And here we want to perform the fill fraction sweep. So we're going to build a series of unit cells where we'll change our threshold parameter across the full range, see what fill fraction we get, and then we can fit that to a curve, and later on when we want to set the fill fraction of the lattice, we can use that curve fit to figure out what threshold value we would need. So we need yet a 3rd grid because our original 2 grids were for the entire 3-dimensional lattice. We want a grid that just focuses on the unit cell. So instead of NX2 or NX3, we'll say NXU, U for just unit cell. So the number of points is the period over the cell spacing on the low resolution grid. In fact, we should do the high resolution grid here, because when we eventually set the fill fraction, it will be on the high resolution grid. So therefore, our grid resolution parameter is the period of the grading divided by the number of points we just calculated. And we'll do this for y and z as well. We will run it, make sure there's no errors, and we can look at how many points will be on this grid. NXU and YU and ZU. 10 by 10 by 11. Then we'll create our axis vectors. We'll call that XAU. Zero to NXU minus 1 times DXU. Semicolon. And then we'll center it about the middle. And we'll do that same thing for Y and Z. Sometimes I wonder if it would be faster just to type it, but as I mentioned, copying and pasting just makes me feel like I'm getting it done faster. Going to run this, make sure there's no errors. Okay, no errors. Now we're ready to go to the next step, which is to build the analog unit cell. The analog unit cell is independent of fill fractions, so we just have to do that once. Then we can use this analog unit cell to do all the different fill fractions. So first we need to figure out how many grading vectors are in the expansion. We know there's only 3, but I don't want to hard code that here, or my code would not be generic. So number of grading vectors, and we can just look at the length of C-list. C-list being the list of Fourier coefficients for each of the planar gradings. Then we can initialize our unit cell to all zeros. And it's a 3D array now because it's a 3-dimensional unit cell. Now we will loop over all of the planar gradings, and we want to add them up. So for readability, let's pull off KX, KY, and KZ from KList. So it'll be the first component of the NK grading vector in that list. So we'll do it for KY and KZ. The Y component of K will be from the second element down, and the Z component will be from the third element down. Then we can calculate our analog planar grading, and that's essentially the exponential of I times K dot R. So K dot R is KX, and it looks like we'll need a mesh grid for our unit cell grid, so we'll go back and do that second. So times XU, that's what we'll call our unit cell grid, plus KY times YU plus KY times ZU. So that is K dot R of our mesh grid. Let's go add a mesh grid before we forget. YAU, XAU, ZAU. Okay, so now we'll have our unit cell mesh grid. We've just calculated the analog grading, so we get the unit cell by adding up all of the gradings. So we'll say unit cell is unit cell plus the Fourier coefficient, which we know is all just ones here, times the analog grading. Let's run it, make sure we don't get any errors. Okay, everything looks good so far. We'll eventually visualize this, but we got to do one more thing. Let's clean up any numerical noise. And at this point, there really shouldn't be anyway, but this is just good for reliability. So we'll ignore any small imaginary components. And then we'll want to scale our unit cell exactly from 0 to 1. So we can do that by subtracting the minimum value. That makes it start at 0, but it could go up to some other large number. So then we divide by the max, and now our unit cell numbers will be limited between 0 and 1. Okay, so let's generate the fill fraction sweep. Now this will be time consuming, so we'd like the ability to turn this on and off. So in other words, we can do it once, maybe save that fill fraction sweep to file, and then we can turn that section of code off and just load that sweep from file, and that will speed things up dramatically. So I just like to do an if one, and then there's an else and an end. So if one, we'll generate the fill fraction sweep in this section of code, And if not, we will load fill fraction sweep from file. Okay, so right now we will be generating the fill fraction sweep. The first thing we'll want to do is initialize our threshold data. So this GTH-DAT, just like we did in computer session 4, we'll do a linspace 0 to 1. That's the full range of threshold numbers. And we'll just use 20 numbers right now. And now we'll set up a loop to tabulate fill fraction data. We'll go back to this analog unit cell, set whatever threshold we have in GTH, see what fill fraction we get, and record that. So we'll initialize it. FF-DAT 0 times GTH-DAT. And that lets me create an array of all zeros the same length as GTH-DAT, but I don't have to worry about the length. So I like doing it that way. Now we set up a loop for n equals 1 to length of GTH-DAT. So for each GTH-DAT, we'll create a binary unit cell, calculate its fill fraction, and record that. All right, so let's generate binary unit cell. UCB is UC greater than GTH dat n. UCB, or unit cell binary, will now just contain zeros and ones. Ones inside the material, zeros in the air outside of the material. Now we'll calculate the fill fraction. So FF-DAT-N. Since UCB contains all zeros and ones where it's inside the material, we simply just add up all of the numbers and divide by the number of points, and that tells us the fill fraction. So we'll use sum to add up all the numbers. We'll stretch UCB out to a single array, then we can sum them, and then divide by the number of points, which is NXU times NYU times NZU. Okay, now the graphics. We'd like to visualize this, so we're going to watch a unit cell grow and grow and grow just to make sure we have it correct. So let's say show unit cell. We won't really know if this is correct unless we're visualizing everything about it. So we'll clear the current figure window. We'll subplot into 1, 2, 1. And here we'll draw, we're going to have two things. On the left, in subplot 1, 2, 1, we'll be drawing our current unit cell. And then on the right, in subplot 1, 2, 2, we'll draw the sweep. And looking at both, we'll be able to tell if this is correct or not. So just for aesthetic reasons, we're going to create a smooth version of our binary unit cell. And we'll use the built-in smooth 3 command, UCB. This is just a blur that blurs over 1 pixel just to smooth it for the meshing. We will mesh the surface of the unit cell. YU, XU, ZU. We are meshing the smooth version of that, and we'll use a threshold value of 0.5. That's right in between our values of 0 and 1. Although after we've smoothed it, the edges will have numbers that are between 0 and 1, and it helps us interpolate where that edge is without the staircasing. That's the purpose of the smooth. Then we'll draw this. We'll use the patch command to draw S. And let's figure out what color we want the faces, and let's do an obnoxious green color. And I'm going to copy and paste these 2 lines of code. They'll be the exact same, except instead of ISO surface, we have ISO caps. And that'll draw the caps on the ends of our 3-dimensional device. We'll give it a view. We'll view it from an angle and elevation angles of both 10 degrees. We'll give it an axis equal tight. Remember, we always would like to look at our spatially variant lattices with equal proportioning. They're weird and crazy enough to look at without that. So we'll keep that here. We'll set our x-axis or x, y, and z-axis limits. The reason we're doing this is because for zero fill fraction, our unit cell will be essentially a little tiny dot in the middle of our grid, and we don't want MATLAB to automatically be sizing the grid, or it won't look like our unit cell to our eyes is changing size. So we'll limit from negative a over 2 to positive a over 2, and we'll do the same exact thing for the y-axis and the z-axis limits. And just for fun, we'll give it some lighting, cam light, so we're shining a camera on this. And we'll give it Phong lighting style, which smooths the edges and gives them a neat reflectivity looking. And we'll give it a title. And we'll call this our unit cell. We also want to draw the sweep. So we'll subplot this to 1, 2, 2, and we'll plot GTH dat from 1 to our current point versus FF dat 1 to our current point. And then we want to set our x-axis limit so MATLAB is not automatically scaling these to fit to our data. We'd like the axis to be fixed, and we just watch the lines sort of appear. It's more aesthetically pleasing. It makes a little bit more sense when you're watching it. So our x-axis will start at GTH dat 1, and it will end at the maximum value of GTH dat. And we'll need a y-axis limit. And this will take from 0 to 1. We know that it's bound between 0 and 1. And let's label our x and y axes. Our x-axis is the threshold value. And our y-axis is the fill fraction. And we also want to force MATLAB to draw these graphics. Okay, we typed way too much code for my comfort. We'll probably have an error, but let's hope not. If this does work, we should see a unit cell on the left that's slowly growing or increasing in fill fraction, and this nice sweep appearing on the right. Let's see what happens. Okay, that's a reasonable trend. That happened pretty quick. What we can do is add more points to slow it down. Let's try 40. We'll stick with 20, but we'll just try 40 right now. Something doesn't look right about that unit cell. Let's go check how we did our list. Okay, no, this does look right. So we'll go back, we'll generate the trend for 20, and then we will move on. Oh, we forgot one thing. Once we generate this trend, we're going to want to save this to file. And that way we don't have to calculate that sweep each time. Now this is pretty quick for this small grid. You would definitely appreciate the approach we're doing here for much larger grids. So save, we'll call it ffdat, and in your computer it'll be ffdat.mat, and all we need is gthdat and ffdat. Now I'll just highlight this line and hit F9, and that is now saved to file. So if we want to turn this off, we would simply come up here and say if 0, so now it won't run all of this code, it'll go immediately to the else command, and now we can load data from file, and we will load ffdat, and we will load gthdat and ffdat. Now we don't have to perform that sweep again. Okay, we did have one mistake up here. Maybe some of you had caught it. we have a KX, KY, that needs to be a KZ. And now when we run the fill fraction sweep, that unit cell looks a lot better. My gut was telling me something was wrong with it. That looks much better. Okay. Now we can turn off the sweep and we'll be loading our data in. Let's run it, make sure there's no errors. Much faster, right? And imagine this for much finer resolution grids. Okay, so we loaded the data in. I would just like, when we load the data in, to show a unit cell and also show the sweep to make sure things are correct. Okay, had to answer my phone. Sorry. Okay, so let's display the unit cell and the sweep. So, tell you what, let's copy and paste the code from up here. Now this is too indented, so I'm going to highlight it and hit Control left bracket, and it brings the indent to the left. All right, and I think everything should work. Let's try it. I don't think we need to do anything else. Oh, we're missing something. UCB. Okay, so we need to recalculate UCB, because remember the binary lattice happened in here inside the if statement, but we haven't done it down here. So let's go ahead and do that. Let's calculate our binary unit cell. We'll copy that code, put that right here. Generate binary unit cell, and since we're not trying to hit a specific fill fraction target, let's just give it a value of 0.6. Let's see what unit cell that generates, and hopefully it's a pretty one. Whoops, we left an N in there. Yes, we don't need to go 1 to N on our second subplot because there is no N. We're not inside a loop anymore. So let's make sure there's no more references to N. Okay. All right, there we go. So we see a nice unit cell, we see our fill fraction sweep, and now we're convinced we're loading our data in correctly. Okay, on to the next section. We have a nice fill fraction sweep. It's turned off. We don't need to do that anymore. Okay, our next section is to generate the input functions, or input data. This is the big three-dimensional array that describes period, the orientation, the fill fraction, that sort of stuff. So period, we'll still call it PER. We'll make it A everywhere, so we won't spatially vary the period in this case. It's a three-dimensional array, and it's on our low-resolution grid, so it's NX by NY by NZ. Orientation. Now here is where we will deviate a little bit from how we did things with the two-dimensional lattice, where there was only really one angle involved, theta. Now that we're in 3 dimensions, we can rotate about a theta or a phi. And I never figured out a way to do that cleanly with like a 3-dimensional theta and phi arrays. So instead, what I found to be a lot more robust is to use rotation matrices instead of an angle theta. So we'll create each point, we'll have a rotation matrix behind it. We'll take the grading vector at that point that we want to spatially vary and perform those rotation matrices on that grading vector. And we do that at each point, and now we'll come away with our K function based on rotation matrices. So in this case, we just want to rotate about the x-axis. We could also rotate about y and z or any other combination, but let's just rotate about the x-axis. Okay, so our mesh grid was centered. So we add half of SY to that to move the origin off to the corner. We want to do a rainbow arcing pattern like we did in computer session 4 again. We don't make it exactly 0.5, we make it a little bit bigger because we don't want the origin of this atan function to be on the grid. We'll get an NAN or an infinity or something like that. So we move it slightly outside, and 0.51 seems to work very well. And we'll do the same thing for the x-axis. And there we go. So we're using the atan function. Now, even though there's only sort of 2 input arguments, y and x, remember this capital Y and capital X are 3-dimensional arrays. So we'll come away with another 3-dimensional array, which shows us an angle that we'll need to rotate about. And in fact, rather than call it Rx, let's call it Rz, because we're rotating about the z-axis, not the x-axis. It'll help us remember that. Okay, so that takes the function or the role of theta in computer session 4, but now we're doing rotation matrices, and that makes it simpler and easier if we're also rotating in other directions. We're not right now. All right, fill fraction. Now this is done on a high resolution grid. Let's go comment on the previous ones that they're on a low resolution grid. So remember why we're doing this grid scheme. We'll do everything up to and including calculating the grading phase. Then we will interpolate that up to the high resolution grid, then calculate our planar gradings in the lattice. So the lattice exists on a high resolution grid, and that's also where we apply the threshold to implement a spatially variant fill fraction. So the fill fraction is on a high resolution grid. And let's make the fill fraction 0.35. And this is on the high resolution grid. So we're using NX2, NY2, and NZ2. So that's it. That's this section. We want to add some code so that we can look at what we've done here to make sure that it is right. So let's run it, make sure we get no errors. Okay, no errors, so we will go on. Show input data. Now we have 3-dimensional functions, and we could visualize those with the slice command or a variety of other ways. I think a simpler, quicker way is to calculate an NZC, which is halfway through the grid vertically, and we'll just image SC the cross section. May not be the best way, but it's simple, and it'll at least let us know whether our input data is correct or not. So we're going to use our image SC technique. Say YA. And remember, image SC plots things upside down. So we'll get a handle to its parent and set the Y direction to normal. The default is reverse. We'll give it a color bar so we know what color corresponds to what value. As always, axis equal tight, and we'll give it a title. And this is PER. Let's run this just to make sure everything's working. Okay, we see PER there. I think I'd like to make this work with our previous plot, so let's go change how we're doing the subplots on those previous ones. Let's make this 221, 222. Now that should make it work so that we see everything. Okay, we see our unit cell, we see our sweep, and we now see the period. It's all ones, at least in the cross section we're showing, but the assumption is that it'll be ones everywhere. Okay, I will copy and paste this. We'll subplot the 235, and in this case we're going to display RZ, that's our rotation matrix, and we don't really need to change anything else other than the title, RZ. And then the last one, subplot to 236, and we want to look at fill fraction. Now fill fraction is on the high resolution grid. NZC is the middle of the z-axis on the low resolution grid. I'm going to use this anyway, which means we're not going to be exactly halfway through the fill fraction, but remember we filled FF with all the same numbers, so in my mind this works just as well. Let's go ahead and run it and see where we are. Okay, and the last thing I usually like to do is to put this RZ in degrees. So let's do that. Divide by degrees when we're displaying RZ. Okay, and we see that everything's correct. Now we're going to be doing some work after this, so if we want these graphics to pop up before the rest of the stuff happens, we will force MATLAB to draw the graphics with a draw now. That's it for that section of code. We now have everything we need to generate our spatially variant 3D lattice. So in fact, that is the next step here. Generate spatially variant 3D lattice. So all of the business for this is actually happening right here. Let's calculate the center of the low resolution grid. We'll need these parameters later. NXC round NX over 2. We'll do this for Y, N, Z. Okay. Let me pause here. Okay, sorry, I had somebody at my door. So we just calculate the center of the grid. We're going to need this later when we're calculating phi. We'll get to that when we're writing that section of code. We are ready to start our main loop, where we iterate over the planar grading expansion. In this case, we only have 3, but if we did an FFT and expanded some other type of unit cell, we would have many more. So we'll call it iterate over Fourier expansion or iterate over planar grading expansion, either way. So we'll calculate how many gradings are in our expansion by looking at the length of C-list. C-list contains the Fourier coefficients. We'll initialize our spatially variant lattice to all zeros. Our spatially variant lattice will be on the high resolution grid. So we initialize it with NX2, NY2, and NZ2. And now our loop, 4NK over 1 to big NK. And that's our loop. The first step in this is to calculate our K function, or construct our K function. So what we'll do is we will grab our specific grading vector, whichever iteration we're in the loop. That's a single vector. We will rotate it according to our rotation matrix, and then put that into a 3-dimensional array of kx, ky, kz that we'll then use to calculate the grading phase. So first, let's initialize these 3-dimensional arrays. And these are on the low resolution grid. So I have one for the x component of k, one for the y component, and one for the z component. We could also initialize these outside of the loop. That might make things a little bit quicker, but for learning purposes, let's keep this group together. So now we enter a triple loop. 4nz equals 1 to big NZ, 4ny equals 1 to big NY, 4nx equals 1 to big NX. So this is a triple for loop over every point in this 3D grid, and we will grab the rotation matrix from that point, rotate our grading vector, and fill in those big 3-dimensional arrays. So the first step is to construct the rotation matrix. So by the way, I'm going to do one other thing here that I like to do when I have triple loops and I don't have any code between the individual loops. I like to flatten these like so. I don't know why I like that better. That's probably bad programming, but I like to do it that way. Okay, so we're going to build a rotation matrix. First, we'll extract the theta from our rotation matrix array. So theta will be the angle that we want to rotate about the z-axis. From that, we build our rotation matrix R. So we have a cosine theta, negative sine theta, 0. Next row in the matrix is sine theta, cosine theta, 0. And the last row is 0, 0, 1. Okay, that is our rotation matrix. Now we're ready to rotate our grading vector. So we'll call it k sub I, the sub I meaning this is just one specific vector from our grading vector list. So by putting the colon here, we've pulled off the vector, but we want to rotate it. So we will pre-multiply by our rotation matrix. Now ki will be that grading vector rotated however we wanted it to at its current position, and so we want to now record that. So we'll fill in Rx at Nx, Ny, Nz, and we'll make it the x component of Ki. And we'll do the exact same thing. Whoops, that should not be Rx, that should be Kx, Ky, Kz. 2, 3. And so that's it. We come out of this with Kx, Ky, Kz being three-dimensional arrays containing our K function. Next step is to calculate the grading phase. So this is easy with our SVL solve command. We just give it the three components of our grading vector. The resolution of that grid, it's on the low resolution grid. And then we'll have our grading phase. Now, just due to how this is solved, our phi could come out with some DC value of phase across the whole thing. And in fact, we're allowed at this point to add or subtract a constant value over the entire grid. And it won't change that other than slightly changing the position of the grading, but that really doesn't have meaning to us. So we're free to add or subtract any constant number across the entire grid. A convenient one is the center value. And that's why we calculated those indices of the center of the grid. Now what this will do is it will force phi to be 0 at the center of the grid, and then we'll force our unit cell to be centered in the center of the grid. So it's sort of an aesthetic thing, if you will. And we're free to add or subtract any value for convenience here, or not do this at all. That is our grading phase on the low resolution grid. Now we want to interpolate this up to the high resolution grid. And we'll do, instead of interp 2 like we did in computer session 4, we'll use interp 3. And that will interpolate our three-dimensional low-resolution phi and make it a high-resolution phi. Now we're ready to calculate the analog grading. So call it GA. And instead of saying exponent I k dot r, that doesn't work when k is a function of position. It's the exponential of I times phi. So it actually becomes a simpler equation. Now we will add that analog grading to the overall spatially variant lattice. SVL is SVL plus GA. However, we want to multiply it by its Fourier coefficient. That's in case we've done a Fourier expansion. This code will still work. So that is actually it as far as the business inside of this loop. We will come out with SVL being our grayscale or analog lattice. Let's add some code inside this loop to visualize what's happening, and it'll look very much like we did for computer session 4, but we're talking about a three-dimensional lattice now. So say show graphical status, and in this case the graphics may be slow. Maybe we want a way to turn it off. You could do an if1 to turn it off. I'm not going to do that here. I'm just going to jump straight into the graphics. So we'll clear the command, or clear the figure window, and now we'll show the planar grading. So we'll subplot to 1, 2, 1, and we'll say image SC. We're displaying something on a high resolution grid now, and we're displaying something that's complex. We want to take the real part of G. Now remember, G is on a high resolution grid. NZC is actually the center of the grid on the low resolution grid, but it's still going to show us some cross section through the lattice. That's really all we want to see. If you really want to see the true center of the grid, then calculate like an NZC2 if you wish, but I'm comfortable with it just the way it is. An apostrophe to get the orientation straight. We want to get a handle to the parent because we want to flip the y-axis. And then we can set y direction to normal. Do an axis equal tight, which we always want to do, especially for spatially variant lattices. We'll give it a color bar. That way we can see if our numbers are exploding. We'll see what values things are. And we'll give it a title. This is the current planar grading. In this case, we only have 3, so we'll see 3 flashes, if you will, of a planar grading. Then we want to show the overall lattice. So I'll borrow that code so I don't have to retype it. We'll subplot to 1, 2, 2, but instead of G, we'll look at SVL. And we'll name this the grayscale lattice, or analog lattice, or overall lattice, or whatever we want to call it. And we'll force MATLAB to draw this. Draw now. Okay, so unless we've messed up somewhere, we typed, again, more code than I'm usually comfortable with. Either we'll be correcting a mistake next, or we'll be looking at it. And of course there's a mistake. We need another parenthesis. Well, we could do it either side of the apostrophe. We'll do it there. And also, since we copy and pasted, we'll have the mistake down here as well. So, another parenthesis. Okay, let's try again. Nothing's happening. I suspect. Oh, okay. Did we get an error? Yes, we got an error. We use GA, not G. Let's go ahead and try running it again. What we should see on the left is our planar grading, and on the right, our overall lattice. Notice how slow this is because we're manipulating three-dimensional grids. Now on the left, this may seem incorrect. We have a our current planar grading appears to be a uniform value. Remember though, this particular grading is oriented in the z direction, so we're looking at a planar grading coming straight at us out of the screen, which means that the planes are in the plane of the screen. So if we're looking at a cross section, of course we will see a constant value. So it doesn't necessarily mean we haven't made a mistake, it's just that what we're seeing isn't incorrect. And we should have our three-dimensional lattice, but the only way really to know for sure is to generate the three-dimensional graphics, which is almost our next step. Let's make sure there were no errors. Okay, all we got was some warnings about the phi solve command, and that's fine. What we need to do first is clean up numerical noise. And so we'll take the real part of SVL, an ideal world that's purely real, but we'll take the real part of it. And then we want to scale this to be between 0 and 1. So we'll subtract the minimum value and then divide by the maximum. When we subtract the minimum value, that means it will start at 0 but end at some arbitrarily high number. So we divide by the maximum, and that will ensure that now it's bound between 0 and 1. Our next step before visualizing the lattice is to calculate the binary lattice, or generate the binary lattice. So we have a three-dimensional array of fill fraction. We need to know what threshold value will give us that fill fraction, and we'll use our curve fit for that. So GTH will be a three-dimensional array containing the threshold values we need to realize the fill fraction that we've defined in that array FF. So we'll use the interp1 command to do that. We give it our fill fraction sweep, but we say, give me the threshold value for what we've defined in this 3D array fill fraction, or FF. And I reshape it to a linear array, so GTH comes out as a linear array. We want to reshape it back to a three-dimensional array. And this is on a high resolution grid, so we give it NX2, NY2, and NZ2. And then our binary spatially variant lattice is SVL greater than GTH. So unless we've made a mistake somewhere, that should give us our binary lattice. So let's go ahead and show the lattice. Show 3D lattice. We actually want 3D graphics here because that's really the only way for us to know that we truly have a nice quality correct 3D lattice. So I'm going to go back up to where we did the isosurface stuff so I don't have to retype that code. Here it is. And I am going to copy that and move it down here at the bottom. So let's do a CLF and no subplot, so this will fill the entire figure window. And this is no longer a unit cell smooth. Let's call this SVL smooth. And so SVLB will smooth the binary lattice. And we're no longer on the unit cell grid, so we have to change these U's to 2's. And instead of UCS, it's SVLS. We'll still use the same threshold value. We'll still use the ugly green. And we'll give it a view angle of 10 and 60. That might look a little bit better. We'll definitely keep an axis equal tight. We'll keep our limits here. We'll do the cam light to give it some lighting. And then the rendering algorithm, we'll use the Phong algorithm that smooths things. And we'll title this our Spatially-Variant Lattice. I should run it now, but there's only one more line of code to finish this out, so let's go ahead and type that, and then we can run it. And what we want to do is save the binary lattice to file. And then in the next computer session, we'll load this up, we'll show it, we'll mesh it, save an STL file, and then in the last computer session, we'll bring it into a CAD program and look at it. All right, so we'll save SV Lattice 3D, SVLB, and we also need the resolution parameters for this. It's on the high resolution grid, so it's DX2, DY2, and DZ2. So that is it. We will have a fully functional code now, assuming we have not made any mistakes, and we'll run it and find out. So it loads in the fill fraction sweep, generates the input arguments. Now is entering the algorithm where it's spatially varying the 3 individual planar gratings. Oh, you know what? We messed up. We only showed 1 unit cell. This is a lattice. Not sure why I did that. So we'll close out of that. Let's just delete these limits here because we want to see the overall lattice. And rather than rerun the whole thing, we can just highlight that section of code and hit F9. And one thing I noticed is that we have not spatially varied anything. Also, I see some end caps here. I think we forgot to change some XU, YUs to X2, Z2. Yeah, so in this line of code in ISO caps, we need a Y2, an X2, and a Z2. Okay, we'll save that. Hold on, let me pause this. All right, I'm back. And we didn't see any spatial variance. Somehow we've goofed in our loop where we're incorporating the spatial variance. Let's see what's going on. Oh, and I see the problem. When we're calculating theta, we're not pulling off the current point. It seems like we're always pulling off the same, the end point. We need to change these to little n x, little n y, little n z. I think that was our problem. Let's go ahead and run it again. Loads in the sweep, generates the input arguments, and now it should start spatially varying the individual planar gratings. Looking much better. We're spatially varying now. Looking good. Alright, let's reorient this. So we can see as I orbit, it looks different. Let's close it. Okay, let's scroll to the bottom. And one other thing we forgot, in ISO caps, we're still using UCS. We need to put in SVLS. Okay. Let's run it one last time. And let's hope we have everything right. Okay, and there's our lattice. Yeah, much better now that we fixed the ISO cap problem. Let's look straight down on it to look at our spatial variance. And what we can see is we definitely have an arc happening. So that's it. We have successfully spatially varied a lattice and saved it to file. So that ends this computer session.